Alright, another draft physics video presentation. So back on Linux Mint 19. Yeah, see, it crashes less. And it actually suspends. So, it is disappointing. I can't find an operating system that I can depend on. But anyway, lately anyway. I figured I'd just go over some of the outstanding points and attempt to contrast them to what conventional theory states, sort of emphatically. We've proven it beyond reasonable doubt, beyond nail in the coffin evidence, and I've pointed out how really bad the evidence is actually. They don't repeat experiments. They cite experiments that are never conducted. They say experiments that are nothing like some other experiment are the same. Like the scatter experiments with electrons is somehow a two-slit experiment when it has nothing to do with slits, and it's not an experiment anything like it. So it's so bad, and it's all about things never considered, and they never really had a debate, and they never did anything in the open, and everything was just decided by some little group of physicists who decide what the truth is. And then they all just fall into place, and everybody just talks the jargon as if. And I don't really get it, frankly. I don't get why physicists happen to be so mind controllable. I mean, you think there'd be a lot more dissidency and some, will to attempt to find a better answer, and they're there to grab. They're simple concepts. So as I've pointed out, gravity turned out to be so simple. I mean, I spent 10 years playing with this stuff, and I had to figure out the fact that you try it and it doesn't work, and you try something else and it doesn't work, and blah blah blah, and then finally you fall on the easy answer. So to be clear one more time, I mean the simple answer for gravity is that matter in the form of electrons and protons. So just call this either one. That stuff, when it moves, it absorbs a little bit of energy. So every time an electron goes from one position to another position, it has to be pushed there. It can't just freely fly in space. So I've made this point that we really don't have any evidence, and we have lots of counter evidence. No evidence that electrons can be shot anywhere, even in a vacuum. You shoot them somewhere and they somehow just don't get there. They have very little mobility. Now, in experiments where they have something complex, like a muon, some sort of electron in some sort of other state, like it might be two electrons traveling together, things like that, they'll call it decay. They'll say these things decay in 2 minutes or 2 seconds, or something. And then they'll say they can change its decay rate, but it doesn't really decay. It just runs out of fuel. It just finally stops. So it has a little more durability. It can go further, but it still can't go forever. It can't go like a wrench thrown into space. It just doesn't keep going. So that's a fact that's sitting out there, that physics really hasn't dealt with, is the fact that they have to keep pushing these things, and they have to push them really hard to get them going really fast. Accelerators use a lot of energy. Okay, they're really expensive. Their fuel bills, because they have to pump an awful lot of energy in to keep these things going. They just can't push them. Alright, bit of a choke and such. Anyway, they can't just keep, push them and then come back 3 days later and push them some more, and then push them, and you're just adding and adding and adding. They lose everything, relatively quickly. So anyway, the idea is that this thing has to be pushed, and the push is actually energy in the universe. Now, this would be perfectly consistent with the notion of their field theory, in the sense that the universe is just full of little spaces in space that have vectors in them, momentum, a piece of momentum, and the fact is that that's what's going to tell an electron where it's going to be tomorrow is what this field of little bits that are going to hit it is. And the idea would be is a little bit has to hit it, it moves it in a direction while it's hitting it. The bit is moving slower than the speed of light. Some percentage, 10% per little bit that hits. Might be 1%, might be 0.0007%, it doesn't really matter. It will move the way it's being pushed until something else happens. Now, if something hits, on this plane, should have been through the middle, but it doesn't really matter. Then it's going to have, that momentum will just add, and so you'll have two little bits pushing, and so now it'll be going, and if let's say it was 10%, then it'll be going 19% because it's 10% of the 90% that was left over. And so it's going a little faster, but still much slower than the speed of light. So both these force bits were going somewhere. I mean, they were off this way. They should be over here somewhere, right? But they're stuck here pushing a big heavy piece of matter. So in a sense, the force, the field, has lost a little bit of energy because it's not where it should be. It's behind. It hasn't traveled the distance at the speed of light anymore. So when it finally gets here, it won't get from here, say before it hit to over here. It's not going to get there at the speed of light anymore. So in a sense, it's lost momentum because it's lost velocity. Now, it never really changed its velocity. It's just being slowed down because I forced it to carry something, so to speak. I did in my diagram. So it'll move this way. Now, if something comes in this way, the opposite side here, an opposite force. Now we have Newton's law. An opposite force is going to act, and what's going to happen is, that opposite force is going to reflect, and one of these is going to reflect to neutralize essentially what you've done. I mean, it's going to undo one of the pieces of momentum, but it can't undo both. So there's still one there, so that means, well, now I go back to 10% the speed of light. Alright, so now one force bit is slowed down. Now if another one hits in from this direction, then this last one flies off, and now you have no motion here. So now we're going 0% of the speed of light. So you get, I think you can follow along, that this simple diagram explains why all motion by electrons and protons is consuming energy out of the universe. The stuff that would be going from point A to point B at the speed of light, now some of this stuff isn't getting there at the speed of light. And by not doing that, every material object essentially becomes, if we assume the fact that it's going to be having motion in all directions, if there's nothing creating an imbalance in the field, if the field is balanced, the argument would clearly just simply be that a certain amount of force is going in and a little bit less force technically is coming out. So the equilibrium is not perfect, and a little bit of what could be called energy has been consumed. So in a sense, you can destroy it, you can use it, and matter uses energy to move. And so that's the simple argument. Now, whether the motion of the matter tends to store energy, because most of the motion an imbalance of the motion will be in the direction of other objects that are also consuming energy. So matter will become closer and closer, and that has an implication that might restore some of the energy of the universe. But you really can't restore it. You really can't make something go the speed of light after you've used up some of its power. I mean, the force is inevitably behind, always, when it has to move matter. It's always, if you took two equal force bits, one has to move matter, one doesn't, they're obviously the force bit that doesn't have to move matter is going to get further in the universe. And so that would be the simple explanation for where this deficit comes from, this equilibrium imbalance that we call gravity. And it's exactly what it looks like. That's exactly what it is like. It's exactly like you're taking a little bit of its presence in the universe, in the sense that it's benign presence in the universe, and making it obviously something that's sucking, it's pulling, it's taking away. It's doing all those things that are, as concepts, you can understand that's what the end result will look like. It's a deficit. So as I pointed out, the real universe is essentially, the empty universe. The universe you think is dark and cold is really the hot place. And these objects are really creating cold spots in the hot universe by being hot, by moving, by jiggling, by having matter move inside of them. And we'll say, oh, it's hot. Well, it's actually cold. Because to be hot, to have stuff moving, means you've absorbed energy from the universe to move. So that simple explanation does the job and does it quite efficiently. All right. The second simple principle is that when this bit of matter moves, it's moving into the universe. That is, it's moving into one piece of it, one side of it, more than he's moving into the other side. Obviously, he's moving away from one side. So any force that's trying to catch this bit has a little harder time getting to it, and any force going this way will meet it sooner than it would have. And so that's could be understood as drag. And protons and electrons are affected by it. Now, the argument would be that regular matter overcomes this drag. That's why you can throw the wrench in space and it'll keep going, because it has a mechanism to fight drag. But the electron and proton don't. I've used a simple analogy for how electrons are producing, in a sense, their presence to the universe is known by the fact that they're just sitting here, like this hand could be sitting here. And if I move the hand towards you, more photons, more light, more energy. If I move it away from you, less photons, less energy, less reality. And the faster I move it, the faster that effect happens. The more transparent the hand not only becomes invisible because it's becoming a smaller source, and you're getting hit by fewer photons because it's a smaller source now. Less percentage, you occupy less percentage of the universe that it's shining to, so to speak. It's also, the faster I go, the less that can catch up to it and reflect off of it and make it visible. So it becomes invisible, essentially, or very visible by moving towards you. And this would explain so many of the physics phenomenons, is the sense that if the electron moves very quickly this way, gets hit by energy, lots of little bits at once, or rapid succession, close together, like a gamma ray. It moves quickly. What it's going to do is reflect a lot more energy this way, and it's going to reflect less energy from this side. So anything going along the same path as that gamma ray isn't going to reflect until this thing stops. Okay, and then, maybe even goes in the opposite direction, then it's going to reflect. So it's moving away from being real in one sense and moving, in one, just depending on what perspective you have. If you're looking at it and it's coming towards you, it's going to look entirely different than if you're looking at it and it's going away from you. And that would explain photons that are created in pairs. Obviously, if it moves, towards you this way, if it goes this way, then this side of the universe, every piece of energy, if it does it very fast, almost the speed of light, you can understand that every piece of force that was heading for it at these different distances, all of those would end up clumped together. It would hit this one, move at the speed of light. It would move at the speed of light to the next one. Okay, hit it. So they'd all end up in a row or in a small amount of space. And then from the opposite side, the exact opposite's happening. A big zero of reflection is happening. So on one side, you have the clumping of the force. On the other side, you have no force. And then if it moves back, you could see that, oh yeah, that's going to be exactly the opposite. This is going to send the clump of reflection, and this side's going to have the nothing. Okay, and so there'll be two equal photons, equal frequency. They'll just be out of phase. The phase will be exactly opposite. When one of them is on, the other one's off. The other one's on, this one's off. Then this one's on, that one's off. That kind of thing. So if you have to look at it through wave glasses, you know, this one's down, this one's up, and this one will be up when that one's down. There's no waves though. It's not waves. So that's another simple principle. Explains why. Now I would argue that photons aren't created by single electrons. A single electron is only sending a piece of what eventually will be a photon, and we kind of know it because photons have a very large polarization. So there's no photons we can create that don't have polarization. You know, they call them unpolarized light, but unpolarized means that it's coming in all polarizations. It just means it's not all in one arrangement. So the idea is that it's like an envelope, you know, or a piece of paper. A photon is coming at you, you know, this way, you know, or this way, or this way, and it's just bits of energy in parallel, you know, traveling the same path. So the bits of energy are all going the same way, and they're all parallel to each other, but they're not in the same space. And this space can be very large. For a visible photon, this could be 1,000 atoms worth of distance between them. And so the real catch, I would argue, the thing that's happening, and we know that you know, metal crystals are what are most interactive with photons in terms of both reflecting them and converting them into other kinds of energy. Electrons leaving the surface, or electricity being produced. And I would argue that the crystals in the metal, so let's just do a simple diagram of a crystal. Let's just say that's a crystal. And it's really dependent on the size of the crystal, because when the photon comes in, okay, these elements, so one electron, you know, created a little extra bit of energy, and then the, you know, more reflection. And then another electron created a little bit more of a reflection. Well, I have to do them in sequence. And then another one did it. So let's just use 3 for this case. And they're flying in parallel. So an electron here on a piece of atom, and then another electron shot another piece, and another electron shot another piece. Extra energy in the universe. And there could be 4 of them here. It doesn't really matter. The point is that they all did it. And if one sent 4 and one sends 2 and one sends 3, well, then you'll make 2 photons, because, you know, you have to have all 3 pieces. But anyway, let's just, for the sake of argument, what's really happening on the crystal is that you're going to hit it with this same sequence. And in doing that, you're going to move an electron in a certain direction. You know, the electron that was here, okay, it's going to get hit with that first one and move. And when it moves, if the second one hits it, okay, at the same time, it'll move that electron faster. And if the third one hits, then it'll move that electron even faster. And that's what shoots the electron off the metal, is that you have to hit essentially the same energy in the direction that it's moving. Okay, so the photon hits and creates a cascade in the crystal, and the end of the crystal is really deciding how many bits of energy you have to hit to knock it out, because it's really at the end of the crystal that the electron will be released, or that the electric current will be transmitted through the rest of the crystals as an imbalance. And what it's really doing is just pushing the electron out of the crystal. Once it's out of the crystal, okay, then the border between the crystal is a hostile kind of area. Nothing can stay in the border, and so it is transmitted to some other place to balance it, and there is no way to balance it, and it just ends up being an electric current. But that would be the argument for the fact that it's a composite object. Photons aren't you know, one blob that just blobs through space, and they know that already. I mean, that this shouldn't even be an argument anyone has to have. They draw it like this, you know, they don't draw it as just this and say, oh, that's a photon there. They know it's more than one. They know it has more than one component to it. So of course, if you're going to convert that into a particles of energy, you would understand it's particles of energy separated by a distance. That's a photon. And again, the polarization is just the fact that the distance is in two directions. They're out of alignment. Their frequency is proportional to their polarization. Because both of them occur essentially created by the speed of light. As electricity travels through the atomic antenna, you know, the atoms of a metal or anything else, what's really happening is one electron moves, and another electron over here is moved by the electricity transferring, and then another electron moves, and that's what's creating the polarization, is the fact that there's time between these events. And the events happen, obviously the first event means the bit of energy is way ahead of the other events, but they're all tied to the fact that there's a speed at which this travels. The change travels through the conductor. And yeah, and so the polarization is just an indication of that, and the fact that it's mixed polarization just means that the crystals are in all kinds of different arrangements, and depending on which way it's arranged, it'll decide which way the photon is polarized. Yeah. Alright, so take a break, move to the next thing. Alright, oops, a quick added bit just in case you know, left it out. I don't want to dismiss drag, but I'll talk more about it later. So you have to, there's this curious fact about the acceleration by gravity, or acceleration anywhere, is that your velocity, okay, ends up being a formula that has a big giant 1/2 in it, okay? So if you want to find out what your velocity is going to be when you're being accelerated, you have to kind of understand that your acceleration is going to be reduced by this giant half number, essentially. So if I push, okay, with a differential in gravity that equals to 10 meters per second of acceleration, right, which is the Earth's gravity. The problem is that if it was just moving these electrons and protons, you'd say, well, why isn't it instantaneous? Why doesn't it just zoom right up to speed? Well, it can't zoom right up to speed. So, so you would expect, okay, that 10 meters per second gravity in the first second would produce 10 meters of distance, that you'd move the objects 10 meters, and you only end up moving them 5. Okay, so their velocity is less than what you would expect. Now, they'll be adding to that, okay, that 5 meters per second. Each second, they'll be adding another 5 meters and another 5 meters, so they'll keep adding, and so that'll become a much faster velocity as the seconds tick off. But the fact is, you're only getting half the value out of the accelerator. So the accelerator is only giving you 1/2 the velocity. And that's essentially the fact that you have to overcome the drag. So as soon as you start to move this electron, it's going to move into more force. And that more force is real. Now it's coming at a rate, it isn't instantaneous, and it's not necessarily completely proportional. So the fact is that it's going to take time for you to have drag you down, to slow you down. It takes time for the drag. Like in the first milliseconds, you might not be hitting any of this force, so you would have the full speed. And then you'll start hitting this, and you'll start wearing down the speed that you acquired through, you know, say a gamma ray is pushing you. It'll take time for the gamma ray to be used up. All right, the components of it. I have to hit a lot of these to reflect all of these bits that the gamma ray has piled up on the piece of matter. And so it takes time to get into enough of the field to hit the extra energy that you're going to hit. And that's why there's this differential. So it's just the drag that creates an obligation that you just aren't allowed to push anything for free. That's the wrong way to say it. Well, I could always try to think of a better way to say it, but I think I'll just move on. Alright, I guess we'll move on now to the other detail. So I'm arguing for a concept of 2 + 2 + 2 physics, that there's only 2 kinds of force and 2 kinds of matter, electrons and protons, and 2 kinds of interactions. And with that simple physics, everything can be explained. Now, you can explain the fundamental part, this part about the drag and the movement of electrons, without dealing with any of these differences. But we so clearly understand, I mean, it's so clear in the evidence that the concept of charge, that there's that there are actual bits in matter that have this opposite property. If I put these 2 things in the same field, they'll do 2 opposite things. One will go away, one will come towards. That they have a completely inverse relationship, and that it's an equal inverse relationship. And so this mechanism of charge, you know, of what electrons and protons do, can also be understood that if I pile up, you know, more electrons somewhere, and, well, I guess the electrons would be down here, actually. If I pile up more electrons and I only have one of the protons, that you would end up creating a charge phenomenon. As you're adding more charge, you're making this more negative, okay? And that gets you to electricity. And that, in a sense, also gets you to magnetism, which is basically the idea that if I take these 2 charges and I could theoretically place them right next to each other, that I would create a dipole, and I would create something that will behave just like a magnet. So I could just say this was north and south just as well, because it'll behave just like that. If I could make another one of those, it would turn and twist and, you know, move into, it would do the same exact things a magnet does. So again, this will add up in the future to explaining magnetism as well. So the simple relationship is that there are 2 forces in the universe. So the little bits flying around come in 2 varieties, just as the electrons and protons do. And the trick is that the electron reacts opposite depending on what force it interacts with. Opposite in the sense that there's 2 kinds of interactions. So if the same force hits, same color, it moves, as pointed out, it sticks until an opposite force causes it to reflect, or it adds even more energy. So it does what I showed in the gravity argument. And it's that simple. I mean, this will reflect when something hits over here, and essentially what you'll see is this bit that hit here essentially is going to be going out this way, and you could say essentially this bit that's been slowed down, pushing this thing for a while, finally gets released and goes this way. That's the simple way to look at it. It's puts the thing, the universe goes back into balance. But if the opposite force hits, if a blue bit hits, it doesn't create any momentum, and it instead is deflected out of one of the perpendicular dimensions. So it goes that way, or it goes this way or that way, and so it's just diverted. And with that simple model, you can understand that if there were 2 red bits next to each other, and there was another red bit between them, that it would be essentially stuck. It would hit this side, stick, then finally reflect, and then go hit this side, stick for a little bit, then reflect, and it would just go back and forth between the 2 objects, essentially creating a variable pressure. So the further away the electrons are, the fewer interactions and the less energy, you would say. So it's just one bit. You could just have one bouncing back and forth, and you would feel the difference. That if I had the 2 this close, there would be, 4 times the number of hits, 4 times the interactions, 4 times the pressure to go that way. that there would, with this, and I have the same amount of energy technically. It's the same amount of energy, it's just one force bit, and yet it clearly creates an effect because you've trapped it, where it's creating more pressure. So, you know, that explains the repulsion of the electrons. The protons would do the same thing with the blue force. And then the opposite scenario, where you put a proton in proximity to an electron, you can see that quite the opposite will happen. Any red force that's trying to get there can't get there, because it's going to reflect eventually. Any blue force can't get anywhere from this side because it's going to reflect. Not that that's, you know, entirely relevant, because it wouldn't hurt this thing anyway. But the important fact is any blue stuck in here, okay, that blue leaves here and goes into this red, it's going to leave here. And any red force that goes into the blue is going to leave this way. So nothing can ever get trapped. Nothing could balance the external pressure, because nothing can sit there and say, I'm going to fight back, I'm going to produce a higher energy because you brought us closer together. There would be less energy the closer they get together. The closer they get together, this gets even deeper into nothing. There's no possibility of anything even getting in here. You could, you know, sort of understand that a blue bit couldn't even, you know, reflect in to this blue bit. The closer and closer they get to each other, there's less likelihood of you know, anything existing in this space. So there was more pressure on the outside, less pressure on the inside. They move together. So it explains the fundamental concept. Now, you know, the simple leap from that charge differential is to understand what a magnet's doing is basically this simple. That, you know, all you've done is you've created a mechanism, the physical structure of the atoms has created there's a bunch of little atoms in the form of those electrons and protons, all pointing in the same directions. So they're all, you know, red, blue, red, blue, red, blue. They're all lined up the right way. And what's basically going to happen is that any blue force that comes in here is going to be turned. Okay, that's what the red does. Any red force that comes in here is going to be turned. That's what the blue does to the red. And so you're going to have a bunch of red that got deflected from up here, coming out here. And then you're going to have the red that came in is going to reflect. So you're going to have twice as much of red. You're going to have all red coming out of the red end, essentially. It's not all red, of course. And you're going to have a lot of blues coming out of the blue end. And so one end's going to push electrons away, one end's going to push protons away. And that's what all the facts indicate does in fact happen. It gets a little trickier you know, when you start introducing a charge to a magnet, because magnets are made out of metal. If I take a charged object, you know, something that's negatively charged with 200,000 volts with a high voltage, that negative charge will charge the metal of the magnet, and unfortunately it'll charge the surface of the magnet, and by charging the surface of the magnet, it'll essentially break the filter that the magnet was. The filter is that it was taking this mixture of red and blue force that's in the real universe, you know, that's all randomized, and it basically segregates it into blue and red, right? So it takes purple and just filters it. And if I put a charge near the magnet, though, the magnet's going to have the pressure from this negative. It's going to push all the electrons in, and it's going to basically just break the surface of the magnet. And likewise, if I put a positive charge, it's going to pull, you know, the electrons out and the protons in. It's going to turn all these magnets back into not being magnets anymore on the surface. And by breaking the surface, you break the filter. That's the simple argument. So that explains why it doesn't work to use a magnet to repel a charged object other than an electron or a proton, because that object will induce an effect that's strong enough to change the magnet, to break the filter, to charge the magnet. All right. Yeah, that's probably enough of that. Because that'll get me to the what can overcome drag. Alright, so what the evidence indicates is that electrons and protons can't be shot through space. They can't come from some other place. Only like a plasma can move from the sun to us, a plasma of atoms that have a bunch of ions, atoms with extra or less than the appropriate number of electrons. But electrons themselves can't fly off the sun and hit the earth. Protons themselves can't fly off the sun and hit the earth. But what can is helium nucleuses. So the idea would be is that something more complex can. So some kind of structure makes it possible. I think this is the bottom. Well, it's not really the bottom. Bottom's even a little lower than that. Okay. Lost my bottom line. Anyway, so there's more complexity has to be built into it. Now, I would argue you can make it, you could do the drawing anyway relatively simple. So let's say the red should be the proton. And you have 2 electrons, let's say. If you could create that mechanism, now a helium nucleus would be more complicated. It might have another, it might have another proton because it's a neutron plus the extra protons, but you don't really need that much. The real key component would just be having these 3 pieces, a neutron and an electron, which would be kind of a hydrogen atom. But anyway, kind of. A neutron would be a composite of a proton and an electron. But anyway, so with this simple mechanism, by the rules outlined, the simple 2 rules, you could understand that the blue energy would end up reflecting back and forth through this mechanism. And and this would get no momentum. So every time the blue energy hits the electron in this direction, right, it's adding momentum. It's pushing it in that direction. Now there's also this attraction because these 2 are, there's no pushing energy on the proton, so there's an attraction between these objects. And but that's balanced by the fact that it's moving. It has to spin or it has to do something to deal with that change in its momentum. So you could understand that it could wobble back and forth. It could do lots of different things, but the point would be, so if you take these 2 vectors and combine them, obviously you could combine them into this as the net motion. The net motion would be this direction. Now if I compressed this object, you'd understand that if I push on these things, that is, it's encountering drag, so I'm moving this thing into space. So it's moving in this direction, right? It's hitting more force in this opposite direction, which is pushing these electrons in here, right? Now the reflection happens much more often. Okay, now they're getting hit more to push out. Now they're getting pushed this way even harder. So the more drag I create, in essence, the more energy I create in the structure by compressing it. So the more I compress, this is like a spring now. So you can sort of understand it's just like a spring, right? The more I push the things in, the more it pushes back. The more I expand it, the weaker it gets. And it's just like the accelerator pedal in a sense. And so every time the drag pushes harder on the accelerator, the neutron pushes back harder. The helium nuclei tries to go faster in the opposite direction because there's more pressure to do so. And so that simple mechanism, it doesn't have to be very complicated, but just this idea of a trap, of 2 ping pong paddles and you got the ball bouncing in between. And if I push one of the paddles into the other paddle, I'll end up creating more force between the 2 paddles and they'll push back. It's a pretty simple concept. And all I have to do is create some kind of disproportion, some lopsidedness in the mechanism, and it's going to have a direction it's going to move in, a preferential direction. And, that's it. So that explains what's taking place when you're accelerating. So when you're, oh boy, I dropped it. when the rocket ship is taking off, what's really happening inside of it, is that all the atoms inside of that rocket ship, all of those nuclei are sensitive to pressure. So the more pressure I put on them, the extra, if I imbalance the field, they turn. So they all start turning, all those little, all the little bits inside that have an orientation, a movement, a direction. They all start aligning with the direction that you're pushing, to find the balance. And they end up all turning in the same direction that they're moving. So they all tend to start going the same complementary direction. And that's why as you keep accelerating, you keep pushing the thrust, you keep pushing more energy into them, forcing them to be straighter and straighter and straighter and straighter. You're just straightening the little engines inside of the matter. And once you've done that, you can turn this off. They'll stay where they are. They have no reason to turn now because you're not applying a force anymore, an imbalance in the force. The river's flowing in just one direction as far as they're concerned, and they're going to stay flowing that way. So once you turn them, they stay where you turned unless you apply a force, unless you push from this side or push from that side, change their direction. And they're just going to keep doing that. And they're just going to keep pushing with that same energy into the drag they're meeting, and they're going to keep just pushing along. And so that's how you give things velocity. So if we could see, if we had a really good microscope, we could see that. We could look at a wrench, on Earth, and a wrench in space, and we could compare the two and look inside, and we could see that the Earth wrench has, these things are moving in all directions, or, well, they're moving actually, they're oriented in the direction that we're moving compositely. You're moving on the surface of the Earth, you're moving through space, the sun's moving, so you have lots of composite directions, but we could see that that one has certain things, and the wrench in space would have others, especially if we give the wrench a lot of velocity in space. Then we could really tell the difference because there'll be a bias in one direction, and we'll see that difference. The wrench that's moving in space is going to have all its little bits pointing that way, and the one on Earth could have them all pointing this way. And the other difference would be there would be a lot more chaos maybe in the ones on Earth than there would be in the ones in space. And such. I mean, obviously, when you throw the wrench into space, you're taking all the motions it already has and essentially combining all of those with one extra motion that changes the direction. So your extra motion has to compensate for the motion it already has. So really, it's just going to be a pattern change. All right, that might be enough. Well, think about whether it's enough and then decide whether it's enough. Alright, summing up. So, I basically demonstrate that there's lots of ways you can model this stuff, and these other models explain the phenomenon really simple. So the idea that there's no free motion, okay, that an object has to actually consume some energy, a matter bit, has to be pushed where it's going to go. It doesn't go for free. But you can, through charge, create a spring, create a mechanism that will allow you to overcome the drag you would run into. And so I guess that's sort of the first rule is that, okay, you can say something like energy must be conserved, but in a sense that's just a statement. The subtle truth is that, it is used up. The universe is less hot because matter's in it. It's just the truth. It progresses through time slower. It moves through time slower because it takes time to move matter. And that when matter moves, a big piece of matter, it's only moving because it's taking advantage essentially of the existence of charge. If charge didn't exist, it couldn't create a spring against drag. It couldn't create a mechanism where applying pressure means more pressure, And so it's really just about the force gets trapped between the matter bits. Trapping matter means you can use it, so to speak. It can do things it couldn't do if it wasn't trapped. It can be variable in the amount of pressure applied. Once you have it in a trap, the trap can vary the pressure that it pushes against the field with. Let's see. Yeah, so there's, yeah, it's not that complicated. Really. And then the whole idea that when you see energy, you're just seeing imbalance. There's always energy. If I take everything out of the universe, it's going to be the most energy you could ever be exposed to will be that universe in terms of real energy. Now the subtlety is that the frequency with which you hit something is all atom dependent. Atoms are sensitive to different frequencies, so depending on how the atom is structured, you can vibrate it in certain ways that'll knock it to pieces, because you can break the electrons from their bonds by adding energy to their resonant system, like that, the little drawing of the electron and proton stuck together. I can break that relationship. I can move the electron enough where the 90 degrees doesn't hit the other electron, and now that's not going to work anymore. So I can break matter and with frequency, but I don't make frequency isn't energy. Frequency is just the same energy at a specific interval that will specifically disrupt certain atoms. They'll all have a different sensitivity to a different frequency of getting jolted. The pendulums all swing. Every atom's pendulum is swinging at a different rate, and you can't use the same frequency to add energy to all the systems. Would be a way of looking at it anyway. Yeah. So it's really, like I said, it really does answer all the questions. You see something in the physical world, you can explain it as just having something to do with the fact that matter has to be pushed. The force has to push it. The force, like the matter, has two varieties, plus and minus, red and black, north, south, however you want to look at it. And there's only two different kinds of interactions, and with that you can answer all the questions. You don't need any bent space, and you don't need any entanglement. You don't need any superposition. You don't need even notions of things being little sparkly bits flying through space, not knowing where they are, or any of that crap. It's a three-dimensional, three hard dimensions universe. Time is just a function. Time is just here because this stuff happens slower than instantaneously. Okay? Nothing happens instantaneously. It takes time for a photon, a piece of energy, a piece of force in the universe to get from point A to point B. If it didn't take time, there wouldn't be a universe. But that's a real thing. It's not a fake thing. It's a real fact, and you're not going to undo it. You're not going to break it. You're not going to remake it into something. It's just, no. We're stuck in the slow universe. The universe. Anyway, so till the next time and such, so forth and whatnot.